Welcome to the Jack Westin MCAT Podcast with your hosts, Michael Maleka
and Molly Hudash. Hello, everyone, and welcome back to the Jack Westin MCAT Podcast with your hosts, Mike and Molly. This is a pretty special episode because it's actually a part 2 of a previous episode. We started off last episode talking about kinetics and enzymes, and there's simply too much to talk about in that realm that we said, pause, let's do round 2, right?
Right.
So what are we talking about with enzymes and kinetics today, Mike?
Right. So we already covered kind of like the basics of rate, right? That's like part 1 was all about what is rate and how it's so different from thermodynamics. Totally different planet. And if you're like, why are they talking about planets right now? Go watch that episode. Go watch. This is, I think, one of those only episodes that we've done so far where if you actually haven't watched the first episode, you should actually pause and watch the first episode. Like the other ones, like you can kind of jump in without too much context, but this is one where haven't watched episode 1, go watch episode 1 of this, the one that's just previous.
Or if you're already very comfortable with rates and what an enzyme is, then it's fine. If you've reviewed this material before, but if you're coming to us to learn content, maybe not for the first time, but maybe for the first time in a long time, go watch it. It will be worth your time.
It definitely will be worth your time because we're going to really be building off because we've covered rate. We're not going to cover too much in depth today, but again, it's all about speed. It's all about kinetics and not about thermodynamics. But we've also covered some things that can impact, right? The different variables that can impact rate. We talked about the Arrhenius equation that kind of shows us. We've talked about our rate equation that kind of shows us how reactant concentration, different orders of reaction. If I'm saying words and you're like, wait a minute, I don't know those words, go watch the last episode.
First order, second order, 0th order.
Right. How does reacting substrate concentration impact it? But then we also
temperature,
right?
Activation.
We also talked about the enzyme, like how enzymes actually impact the rate, because we know they impact rate, not favorability. We made that distinction very, very clear. If it's not favorable to start, adding an enzyme is not going to do anything. All it does is speed things up. And how it does that? Lowering the activation energy, making it so you don't have to invest as much energy in to get over that hump, to get over that kind of that hill of that high energy intermediate. And then we talked about, what actually is this enzyme, this big ball of amino acids, right? This big protein, the different sites that are important. And so we're really jumping in today on enzymes and actually how we study how enzymes impact rate. So Molly, we're going to be chatting about Michaelis-Menten. We're going to be talking about inhibitors. I'm excited.
And Lineweaver-Burk.
I know you really like the Lineweaver-Burk plots. And again, something that so many people really dislike. So I'm happy that we're going to talk about it. And someone who's as passionate about it as you are is going to be chatting about it.
Well, here's the thing. I feel like there's this misconception with a lot of, at least students that we see in classes. I assume this applies to podcast listeners too, but when students come to class, I think there's this expectation that the people that are teaching the classes or hosting the podcasts have just, they were like born with this knowledge. Like they never had to struggle for this. But that is so not accurate, right? And all the things that I personally get really pumped to talk about are the things that boggled my mind when I first started, right? Or the things that I had trouble making sense of. I had trouble memorizing. Again, not a memorization person. So the things that bothered me initially are the things that now I love, right? But I feel like it's valuable to point out that no one was born with all of this knowledge. And I mean, you don't even have to be this walking encyclopedia to get a great score anyways. Maybe you weren't born with it, but you also don't need to be that, absolute chemist, physicist, genius in order to score well, right? That's the beauty of the MCAT. So yes, we will talk about Lineweaver-Burk. In fact, I love all of enzyme kinetics. I'm super excited to get into this, but I feel like, as you mentioned, we covered a lot last episode. And there's one thing in specific that I feel like is super relevant to what we'll talk about today, especially when we talk about inhibitors later. And that's just the sites on an enzyme, right? So to set our stage, an enzyme is a protein, big, long chain of amino acids. This is a protein that's specialized to catalyze a reaction. Like you said, it's not a thermodynamic, thing. It's not a thermodynamic beast, I think is what I called it last episode.
Beast. Yeah,
right. it lives in kinetics land, right? It's very much based on speeding things up. It does not have any effect on equilibrium, like you mentioned. If it's a non-spontaneous reaction, it can't suddenly cough up the energy to get that to happen itself, at least. What it can do is reach out and grab onto a substrate, right? That is going to enter the binding site. That's part of the active site. And then we will see some sort of catalytic reaction. The enzyme is helping speed up the reaction, not by being an active participant, but by helping the uncomfortable transition state where you're half enzyme and half substrate and half product become more stable. Okay, so when we talk about an enzyme, the active site is really where the magic happens. That's where the substrate is going to bind and undergo that catalytic reaction. There are other sites all over that gigantic, often globular protein, this big ball, twisted
Big
ball
ball
of
of
amino
amino
acids.
acids.
Sometimes multiple peptides in there too. Any other site on that enzyme that's not the active site, it's not where the substrate binds, could theoretically act as what we call an allosteric site, right? Allo is other, steric is place. So allosteric is another place on the enzyme that's not binding the substrate. This sounds abstract now, but it's going to come into play very specifically with inhibitors. So that's the one part of last episode that I want to make sure, even if you listened, that we're comfortable with that idea, an active site versus an allosteric site, because that is what all of inhibition is built on in a way. But right, the rest of it, go watch the episode. Today, I think the best place to start to pick up where we left off in kind of joining these two topics of enzymes and kinetics is with Michaelis-Menten.
I love Michaelis-Menten. I
know.
love Michaelis.
And I'm excited because I feel like we have very opposite things that excite us. And I know that you really love the math of Michaelis-Menten and the research of Michaelis-Menten.
Yes, yes.
So tell us the story of what's going on.
Of course. Again, because I resonate so much with like these are things I didn't understand, so it never really made sense at first. I was so confused. I think the biggest misconception about Michaelis-Menten plots is all just one experiment, right? It happened just one time. But no, let's take us back to actually what happened. So way back, I don't have a date, but we wanted to study how substrate concentration impacted the reaction rate. We wanted to see if I change substrate concentration, how would that impact the reaction rate of an enzyme catalyzed reaction? We understood 0th order, first order, second order, but we want to see, okay, how does an enzyme change things? So what they did, so Michaelis-Menten, I actually don't know if these were two people, one person. This I don't know. Well, I think it was two people, right? But what they did was that they took the small vial, and added a measured amount of enzyme to that small vial. Let's say 10 molar. And then if there's 10 molar enzyme in this small vial in this solution and there's no substrate, would there be any reaction? No, there's nothing to react. But what they did was they added a very small amount of substrate, a very small amount, and then they measured the initial reaction rate and then stopped the experiment, right? Only the initial reaction rate and plotted it. They then did this entire thing. They threw out that vial. They were like, okay, we're done with that. Made a whole new vial, had the exact same concentration of enzyme, and then added a little bit more substrate, measured the initial reaction rate, and then stopped the experiment, plotted that. And they did that over and over and over and over again. And what they found was that at first, when they started adding more substrate concentration, the initial reaction rate would go higher. We'd have a much faster initial reaction. Of course, because now these enzymes have all this substrate around that they can grab on that they weren't working, now they can. But this very strange thing happened where as they started adding more and more substrate concentration, the increase in initial reaction rate would still go up, but it won't go up by as much. And eventually they got to a point where they started adding substrate concentration and that wouldn't impact their reaction at all. The reaction rate would be the exact same, even though they doubled, tripled, quadrupled the amount of substrate concentration. And then they plotted this data. And this is where we get the Michaelis-Menten graph, this hyperbolic curve. Again, I want to say that word because that's a word that we do need to know. It's this hyperbolic shape where at first it goes up as we increase substrate concentration. That's our x-axis. That's what we're increasing. We're increasing it. And our y-axis is the initial reaction rate. And we see that at first it's going up and up, but then it just levels out no matter how high you go. Now, this is the idea of Michaelis-Menten, and why it's, in my opinion, in my thoughts, it's very important to know how we got the curve. Because if you think this is one experiment, it makes no sense whatsoever. No sense. How are you changing substrate? How are you having changing initial reaction rates if it's just one experiment? No, this was multiple experiments done again and again and again. And so I think it's so cool because now it makes sense why it looks the way that it does. And from this graph, there's some important points. But kind of before we talk about the really important parts of this graph, I like kind of hitting on the y-axis because there's something I said very intentionally a lot, which was the initial reaction rate, right? This wasn't just any reaction rate. They didn't wait 5 seconds, 10 seconds, or waited even to equilibrium. They only measured the initial reaction rate of these experiments. But then the thought needs to be, why? Why did they do that? It's because when they wanted to see how substrate concentration affected that forward reaction. But if you wait 5, 10, 15 seconds, what happens is you form product and the reverse reaction occurs. So if you wait 5, 10 seconds, you are only seeing the net reaction when you're looking at these vials. So you're not actually measuring the forward reaction anymore. You'd be measuring the net of the forward and the reverse. So then maybe the forward reaction is 10 molar per second. But if you waited 5, 10 seconds, the reverse reaction might be 2 molar per second. So what you'd measure is actually 8, which would be incorrect when in reality it was 10. And so this is that really important note that this is not just any reaction rate on the y-axis. It's the initial reaction rate. It's important because of that reverse reaction. Again, I nerd about this. I'm start getting rambly because I just love talking about this. But this is kind of when we look at a Michaelis-Menten, it's important to know how they got that graph in the first place.
Yes. Yeah. And I love the history lesson. I tend to go way, way back in evolutionary biology. And I like that you get excited about this. And I like that you point out the initial reaction rate. And also, just to really reemphasize this, there's always the same amount of enzyme in it. We're not changing the amount of enzyme that's in that vial. It's always at a set concentration. And then we're changing substrate concentration, right? And we've got on the x-axis of this graph, right? It is substrate concentration. So whatever substrate we're interested in. If it's a multi-substrate reaction, right, we look with respect to each one individually. So you have substrate concentration on the x and then initial reaction rate, as you said, on the y. So cool to think of how wonderfully frustrating that must have been to plot. But again, we end up with this curve. And for me, I love connecting this to rate law because it's really, really cool to think of what happens. We start out with basically a linear relationship. As substrate concentration increases, when we consider the shape of the curve, right, it's almost linear, right? Increased substrate and reaction rate goes up a lot. And then, as you said, it starts to kind of level off. And actually now you might add more and more substrate. Maybe you add twice as much substrate, but you only increase a little bit. Right? You don't increase double like you would earlier, right? It levels off and then it gets flat. It's really cool. Back when we were talking about first, second, and 0th order reactions, right? We start off linear-ish, right? That's a first order reaction, right? As we continue, it levels off to a 0th order reaction, right? Because changing substrate concentration does nothing to rate. And a lot of students ask, why? Why does it level off? What is the meaning of that, the slope of the graph changing? And I think the important key piece here is you're not adding any more enzyme, right? I personally, the thing that makes me, well, one of several actually, that makes me so excited about enzyme kinetics is we think of this maximum rate that we can get, the fastest that rate can get as this one objective number that never changes. Like, the Vmax of this reaction is however many reactions per second. Like, we have it in our mind that you can't never change that. And Vmax, again, would be the point that we don't really cross. When we increase substrate concentration and we keep increasing it, we level off, right? We get horizontal, parallel to the x-axis. We never go higher in our initial reaction rate. And that actually happens when our enzyme is completely busy. And I love this because I think of enzymes as, you know, and Mike's gonna laugh because I always humanize my biochemistry. But like, I think of an enzyme as a individual person, right? An enzyme is capable of carrying out a task, right? You can, if you're doing nothing and you get a homework assignment, you could do it, right? No problem, right? If you suddenly got 2 homework assignments, okay, you could still probably do it, right? 3, okay, this is more now, but like you could still do it. There's a point that you cannot work that fast. Like there is a inherent limit to how much you can do and how fast you could do it. Every human being has limits. We only have 24 hours in the day. There is a limit. And enzymes are the same way. As an individual, they have their own maximum speed of work. This is as fast as I can physically work. That is not Vmax, right? For an individual enzyme, this is actually what we call kcat, or the turnover number. It's the maximum rate of reaction for one enzyme. And that's kcat is unique to the enzyme, period. One enzyme can only work so fast. When we look at Vmax though, that can actually change. We can change Vmax, and we can imagine this if, right, considering that test tube reaction, if we only had one enzyme in there, right, you can map that whole reaction, but you're going to reach the absolute maximum pretty quick because you only have one enzyme and it can only do so much. What would happen if suddenly I had 2 enzymes in that test tube, or 4 or 6 or 8? You now have, in the same period of time, 2 or 4 or 6 or 8 times greater capacity to catalyze that reaction, because every individual enzyme can work that fast, right? And that is the basis of Vmax. Vmax is objectively the rate, how fast one enzyme can work, times essentially how many enzymes you have. It's enzyme concentration. But we can change Vmax based on how many enzymes were there. So hypothetically, in your experiment, as we were describing it, right, we reached this point where to our little test tube with the same amount of enzyme that we've always had, you can add substrate, add double, twice, or double, triple, quadruple the amount that you had in the previous experiment, and it does nothing to your Vmax. If instead you doubled the enzyme concentration, you would be able to achieve that fast growth again. You can move your Vmax, right? You could change the shape of your graph, because at Vmax, you have individual enzymes that are drowning in substrate, right? Imagine you're a student and you've got 600 homework assignments. You can't snap your fingers and do all of them. You can work as fast as you can. You can keep chipping away at things, but at the end of the day, there are limitations, right? The only way to change Vmax is to change the amount of amount of enzyme that you have, so that there's more hands that can complete, in that case, the assignments, but really this, catalyze the substrate reaction at a greater extent. So I love that stuff.
I the way you explain it, like how you prefacing with kcat first, I think is really cool, because you're totally right. People, we think that, and again, I know I thought about like first like this, like Vmax is just this solid thing that can't move, right? Because that's what we're used to on a Michaelis-Menten graph. But we have to realize, in a Michaelis-Menten graph, enzyme concentration would stay the same throughout. But if I change the amount of enzymes, it's like I have more workers. I've got more people doing work. Vmax is just the total work that's happening between all of our enzymes, right? But if you just make more workers, more total work is going to happen. And then thinking about kcat as like the maximum work of a single enzyme. I think if you define kcat in that way, well, it just, of course, makes so much sense. And again, this is, I think, going back to this idea of not memorizing, because I'm sure a lot of people here who are listening probably memorize the kcat equation. Kcat is Vmax over enzyme concentration,
which I hate also.
Right, but I think if you take it as Vmax is just kcat times the amount of enzymes.
Enzyme concentration.
Right? Like you don't have to memorize the other equation.
In that way,
It's the exact same equation, just rearrange
it
a little bit, but it makes make a lot more sense, right? It's more intuitive in that way. And that's what I always kind of like. I'm actually a really big fan of rearranging equations to make them intuitive, to help me understand them rather than memorize them. Again, it might not be the way that my equation sheet that I memorized kind of wrote them out, but if you can rearrange an equation to make it intuitive rather than memorizing, do it. As long as you're not changing the equation. Please,
Yes, as
people are
long as the math is the same.
as long as the math, don't like start adding variables. Like, no,
Yeah.
please don't do that. But if it's the
Yeah.
same equation, yeah, rearrange it. I do that for we haven't talked about the index of refraction equation, like the
Yeah.
n equals c over, I do that one. I rearrange that one to make it make more sense to me. But yeah, we can talk about that another day.
At another time.
But
Yeah.
but that's absolutely this Vmax, right? And kind of going back to the Michaelis-Menten curve, was that maximum initial reaction rate. When Michaelis and Menten kept on doing the reaction, adding more and more substrate, that was that initial reaction rate that did not move. That no matter how much more substrate they added, those enzymes couldn't work any faster, right?
Yeah.
And so that Vmax is a very important value when it comes to Michaelis-Menten. But there's another important value we do need to talk about, which is Km, right?
Yes.
And so I want to preface, when it comes to Ks, right? Again, I did not make the rules of chemistry. There was somebody who really loved the letter K in chemistry. They love that letter because we've talked about a few Ks already, like over the last, however many podcast episode. We first talked about big capital K, the K equilibrium, concentration of products, concentration of reactants. We've just talked about the rate K, the slower case K, which is all about the rate constant. Now we can talk about another K, which is Km, the Michaelis constant. And now here's a kind of a big nuance thing. It is a capital K. It is capital K, but it is not an equilibrium constant.
Yes. It's the only exception to that rule. Big K, small subscript. It's a type of equilibrium, except Km.
This is the only one.
Km. The only one.
And this is the one where I notice a lot of students when they're like doing their passages, they see capital K. The first thought is oh, it's like Km, right? That should not be the first thought. It's like that saying, when you hear hooves, think horses, not zebras, right?
Yeah.
You see a big K, you should first assume it's probably an equilibrium constant, unless there's something to tell you that this is a Michaelis constant. Don't first jump that's a Michaelis constant, because that's the exception, not the norm, right? But let's talk about what this Km value is. So Km is defined as the substrate concentration to reach 1/2 Vmax. Now, I want to kind of clear them. Km is not 1/2 Vmax. It is not the 1/2 Vmax. Because that's, I hear a lot of people, it is not a reaction rate. Km is the substrate concentration that you need in order to reach 1/2 Vmax. Now, this idea is very important because we have to realize then, based on that definition, what would be the units of Km?
It would be substrate concentration, molar, something like that.
It'd be molar, right? Some millimolar, nanomolar, whatever. It's a concentration. It's not a rate. It's not inverse molar, right? A lot of equilibrium constants are inverse molar, but that's just based on the equation. But no, if you see a capital K with the units of molar, now this makes you think that this might be a Km. But otherwise, like if it has no units or units that are non-1 over or that are not molar, it's an equilibrium constant, like flat out. So Km defined as the substrate concentration to reach 1/2 Vmax. But then the question needs to become, why do we care about that
what's
value?
the point?
Yeah, what's the point? Like, okay, you've told me how much substrate I need to get halfway there. Like, okay, why is that important? Because when you think of Km, the word that should come to mind is affinity. That's the word. And what do we mean by affinity? Affinity is just how we kind of frame how badly does this enzyme want to bind to the substrate, right? How much does it like binding to the substrate? And we use Km to tell us that information. Because imagine with me, Molly. I need just, like you're imagining right now, imagine I'll add a little bit of substrate. Like I put a drop of substrate in, and then my reaction rate shoots up to 1/2 Vmax. Right, it shoots up. So do my enzymes, when they saw it, were they like picky or did they like grab it right away?
Oh, they grabbed it. They were very excited about it.
I added just a little bit of substrate and they shot up. But I want you to contrast that to if I had so much substrate in order to get to that 1/2 Vmax. Were my enzymes excited to bind to that substrate or were they like kind of picky about it?
They're pretty picky.
They were really picky. And this is how I like to frame Km in terms of affinity, where a low Km means a low amount of substrate to reach 1/2 Vmax. Tell us that is a high affinity. Low Km is high affinity. They have this inverse relationship, whereas a high Km, a high amount of substrate to reach 1/2 Vmax, is a low affinity. They're kind of picky. They don't want to bind to that substrate as much.
I always gotta humanize things.
Of course.
I always explain this as a procrastinator. There are two kinds of students. There are the students during syllabus week that first week they get one assignment that's not due for 2 months and it's done the next day. Like they have,
but okay.
This is very like it. everyone knows at least one of these people. It's not really me either, but like they're excited to do the work. They're excited. This is a class they care about. Like, I don't care that it's not due for a very long time. I'm going to do it now, right? I have a very low amount of work to do and my deadline is not very present, but I'm very drawn to the work and I'm going to do it, right? That is a very self-motivated, right, high affinity enzyme that would have a very low volume of work necessary to get it to 1/2 of its max speed, right? So again, low Km means that you only need a little bit of work or of substrate in order to get you moving fast, right? On the other end, right, where probably several of us fall,
including
right,
myself,
the procrastinator's end,
right?
right? You get through syllabus week, you have an assignment that's not due for a while, and you're like, okay, I don't care. And then you get another assignment the next day that's due in like 2 weeks. You're like, okay, still not really going to do anything. Then you get another assignment, right? And it kind of piles up. And then you look and you're like, okay, actually, there's a lot to do. Now I'll start working, right? You do not have a very high affinity towards that work. Again, the Km in that case, your affinity is going to be, or your Km, I should say, your Km is very high because you have to have a lot of work or a lot of substrate around you to get you moving, right? And keep in mind, the reason why we say 1/2 Vmax is because every enzyme, and again, different concentrations too, Km can change, right? So rather than saying like how much substrate is necessary to get you at X amount of reactions per second, right? That's some enzymes may never move that fast, or some enzymes may move that fast even like almost at rest, right? We use 1/2 of that Vmax of that reaction so that we have a way to describe affinity that's not really dependent on whatever that Vmax value is, right? It's
if
basically
the Vmax changes, that 1/2 Vmax is going to change.
Exactly. Yeah. So it's allowing us to describe the affinity. Again, if you have a very low Km, you need very little substrate around to get going and to start working. You can get to 1/2 Vmax. That's a very high affinity. And the reverse is true of our procrastinators. High Km, very low affinity. And that kind of draws us nicely to the idea of catalytic efficiency.
Oh my goodness. I get so heated about this.
Oh, I'm excited.
Because no, honestly, no, you go. You go, please.
Let me just lay the groundwork, okay? Because I want to see you, crash out over this.
Yeah, I'm about to crash out.
Okay. Catalytic efficiency is this equation that we can use to help us understand how well an enzyme works, in essence, right? Km and Vmax are going to be specific values, a substrate concentration or a reaction rate. And those are hard to compare between reactions, right? And between different enzymes that do different things. So we have this equation, catalytic efficiency, that is going to take into account Km for that enzyme and also kcat. Not Vmax, which is concentration dependent, but that kcat, that's how fast can this one enzyme move, right? Or else you'd see different efficiencies for, solutions that had different concentrations of enzyme. No, kcat and Km, right? I always assume, in order to help you remember, it's a ratio. If I want a very efficient enzyme, I want a super high kcat, because that means you move very efficiently. Or very well, very fast.
Don't say that word.
I know, very fast. You're able to catalyze the reaction fast.
Right.
And then a low Km, because you want it to be high affinity. So catalytic efficiency, if you want to max it out, kcat is on top, Km is on bottom.
Right.
That's the basics. Now let's hear the crash out.
I'm about to crash it because I want everyone listening to never, I'm about to make a statement and you are never allowed to make this mistake. Anybody listening. Kcat is not equal to catalytic efficiency.
Yeah.
Kcat is not the catalytic efficiency. Oh my goodness. We've been doing this for years. I hear that all the time, right?
Yeah, it kind of breaks my heart.
Right. Oh, kcat's the efficiency. Absolutely not. Kcat is the turnover rate, right? It's the speed of the reaction rate of a single enzyme. The efficiency is how efficient that enzyme is. But the way I like to preface it is, like, let's take a scenario. Let's say I have an enzyme that can, once they bind to the substrate, can move really fast, but it takes forever for them to bind. Is that a very efficient enzyme? No. Let's take it on the flip side. Let's say I've got an enzyme that binds really, really well, but takes forever for them to actually catalyze that reaction. Is that an efficient enzyme? No. So you have to take both the speed of turnover, that turnover rate, and the affinity into account. And that's where catalytic efficiency comes from, where you have to take both the kcat and the km into account. But again, I always, whenever I teach a class, I make everyone in the chat say this: kcat is not the catalytic efficiency.
Yes.
Please don't make that mistake. I'm about to crash out if I see that mistake one more time, because I just see it way too often. But
Yeah. Yeah. It's also funny or not funny. It's wild as an instructor, because over the years we've worked with so many different students, and we see students come in that pretty much for the most part have very similar issues and misconceptions to begin with. So it's like we see this problem again and again and again,
over and
always
over
with
again.
different students, but
Mhm.
we see the same
You-
pattern play out. And yes, I've seen that many times too.
You're all thinking, oh, Mike's just being exaggerating. No, when you see the same mistake hundreds of times, you're like, I don't want to ever see this mistake again. So you've all been warned. You've all been warned. kcat is not the catalytic efficiency.
That's nice and ominous. You've been
Yes.
warned.
You've been warned.
Okay, so let's steer clear of the catalytic efficiency
Sure.
discussion now that we've got threats on the table.
Right.
Let's talk about probably the reason why some of you guys are listening, which is Lineweaver-Burk. And this is kind of, it's similar. It's bringing back electrochem vibes from our previous episodes. How many people are scared of Lineweaver-Burk? Just like so many people are really scared of electrochemistry. But really, Lineweaver-Burk is so easy once you've laid the groundwork that we already have.
Somebody just got triggered right now, but just by you saying that, they were like, easy?
With
What are
the
you talking
groundwork
about?
being laid right now. And if you don't believe me, let's prove it.
Right, we'll prove
right?
it. Right.
Lineweaver-Burk plots have, and I'm going to hold everyone's hand while saying this, the exact same information that's in a Michaelis-Menten plot. Except, let's say if you want to find the Km, you don't have to look at the X or the Y axis that has the Vmax, right? You don't have to find the place where it flattens out and then carry it over, find Vmax, and then calculate what's 1/2 of Vmax, go here, and then follow that over, find where it intercepts the curve, and then drop it down to the X-axis to find
That was
Km.
a lot of steps, and I'm
It's
like,
a lot of steps.
yeah.
It is a lot of steps. It's not that hard. Students can, most students
Could do
are
it.
comfortable with Michaelis-Menten, but it's a lot of steps, and there's a lot of opportunity to go wrong. Lineweaver-Burk, what they have done is take the Michaelis-Menten equation that plots that curve, right? They've taken that equation, and on both sides, they've done 1 over. It's what we call a double reciprocal plot. And I know there are people that are like, why the heck would you do this? That makes things way more complicated. Instead of X-axis being substrate concentration and Y-axis being that initial reaction rate, it's now 1 over substrate concentration and 1 over the reaction rate or the initial reaction rate. Is that annoying? Yes. But it also gives the most convenient plot type. It's a line.
A straight line.
It's
Who doesn't
just a
love a
straight
straight line, right?
It's a straight line. And the beauty of Lineweaver-Burk, again, everything that we just talked about with Michaelis-Menten is exactly the same. Vmax, Km, that all the values we talk about, the ideas we talked about, it's all identical. Lineweaver-Burk is the same thing, except you flipped both sides of the graph. Now we get a line. And rather than having to go through all those steps to see Vmax and Km, you can actually see them. They are the X and Y intercepts.
Right.
It's
right.
beautiful. I love it.
It simplifies it so much because you know exactly where to look. You don't have to try to do all these calculations. You just know if I need Vmax, this is where I go. If I need Km, this is where I go. And it makes life so much easier. So let's say, Molly, I need to find the Vmax, right? You just said it makes it so easy to find the Vmax.
Yes.
Where would I find that?
So you'd think about it first, right? The X and Y axes, right? X is 1 over substrate concentration. Y is 1 over the initial reaction rate, right? Vmax, is that going to relate more to the reaction rate, the Y-axis, or the X-axis 1 over substrate?
This is a tough one, but I'm gonna have to say the Y-axis.
It's a trick question, but yes, the Y-axis, right? And I just said that Vmax and Km are described by the intercepts. So we're probably going to be looking at the Y-intercept. The only thing that we need to be really careful of is that the Y-axis is actually 1 over the reaction rate. So what we're going to see, the Y-intercept is 1 over our Vmax. Okay, but that's it, right? You find it on the graph. And I mean, you don't very frequently see them asking you to calculate Vmax from a Lineweaver-Burk. Most often when you see these, they're going to be used for inhibitors. And to be honest with you, inhibitors in Lineweaver-Burk, very scary at the beginning because you're just trying to memorize, oh, an uncompetitive looks like
shapes.
this, the
Yeah.
shapes. Once you clue in to x-axis is
Mm-hmm.
describing the km,
Mm-hmm.
again, it's 1 over the km. And actually, based on the fact that the line crosses both quadrant 1 and 2, it's actually negative 1 over the km.
Yeah.
But you can't have a negative substrate concentration. So you drop it, right?
Right.
The fact that the x-intercept represents km and the y-intercept represents Vmax, you can do those Lineweaver-Burk questions with inhibitors super fast. And that's what they're more likely to do for you. But that's how you'd find Vmax from Lineweaver-Burk. And the exact same process is true of km. It's just find the x-intercept, 1 over, of course, technically it is to the left of 0 on that number line in the graph. So you drop the negative sign again. No negative substrate concentration.
Right. It's very cool when you look at the data plotted on Lineweaver-Burk. It's all in the positive quadrant. Like there's no actual data points in the negative area. They've just extrapolated the line. Like that's the kind of key. They've just extended the line down. It's not like they had data points on that side of the graph. If you actually looked at the data points, they're all on the right side.
Yeah. Yeah, because you can't have negative substrate concentration.
Right, you can't. That's impossible.
That doesn't make sense.
Doesn't really make sense. But yeah, but again, really realizing, and again, this is where I like the math about it, because all they've done is they actually took the Michaelis-Menten equation. Now, if we can put it up on the YouTube video, we will. Again, I'll leave that to the editors, but I'll just say it verbally as well. From the Michaelis-Menten graph we talked about before, of course, if there's ever any plot, we have to have an equation for that plot. So the Michaelis-Menten equation is initial reaction rate, which is that y-axis. Again, on the Michaelis-Menten plot, we're not talking Lineweaver-Burk right now. Michaelis-Menten is V naught equals, it's a fraction. On the top part, in the numerator of the fraction, it's Vmax times substrate concentration, and the denominator, so that's over Km plus substrate concentration. So this is our Michaelis-Menten equation, and that's what we generated from the Michaelis-Menten prop. All those experiments, we drew a line, we're like, okay, what's the equation of this line? So we can actually calculate using these variables what V naught is. But when they took that double reciprocal, all they did was take the inverse of that plot. So they just flipped both the y-intercept, both sides of the equation. So it became 1 over V naught equals Km plus substrate concentration over Vmax times substrate concentration. They did some great math there. And again, whenever I teach this in class,
I like students are glazed. They're like,
I'm like,
huh?
I hope we can get a picture of this on the video. But what they ended up finding was an equation, the Lineweaver-Burk plot equation, which is just y equals mx plus b. That's how they plotted it, which is just an equation of a line. And so I like practicing about that. Again, I want to write things down, but I can't. But I guess it is good to know what the Lineweaver-Burk plot equation is. But I mean, you can just learn that from the graph if you kind of think about it. So the y is the y-axis, 1 over V naught equals m, which is the slope. And now we haven't talked about that, but that's Km over Vmax. And so that's
also, if you don't want to memorize, just do rise over run from left, from x-intercept to y-intercept. You can calculate it. You don't need to memorize.
You don't need to memorize it. So that m is just the slope, which is just rise over run, which is Km over Vmax, times x, which is your x-axis, which is 1 over substrate concentration, plus b. And b is on the y equals mx plus b equation, the y-intercept. So that is 1 over Vmax. And so I'm a math nerd, so I love the fact that that equation just plots really well to that graph. And you don't even have to memorize the equation. The graph can get that from the graph, knowing what those points are. But just really realizing it's the exact same stuff. They literally just rearranged the equation and then they just replotted it. No new data. It's not a whole new experiment. They didn't do they just took Michaelis-Menten's work and just like, hey, let's make it our own kind of deal.
Yeah. Yeah, very literally. So hopefully we've won you over on Lineweaver-Burk. Again, it is incredibly fast to navigate once you know what you're looking for. Rather than having to go through all these steps, you just look at x-axis or x-intercept, y-intercept, and you're done. When we talk about inhibition, this is going to become even more important because what we are going to see is that these inhibitors are going to change our Km and Vmax in characteristic ways. Okay, we're going to talk about a couple different types of inhibitors, and they each have a unique pattern of what they exactly do, what they bind to, whether it's the enzyme alone or the enzyme with the substrate, right? Where they bind on the enzyme, right? Their unique pattern of, or their unique mechanism, I should say, determines how they change Km and Vmax. And when you're trying to figure out what the reaction would look like, or what the Lineweaver-Burk plot would look like with and without an inhibitor, the beauty is if you know that a particular type of inhibitor, let's say, decreases your Vmax, find the plot that has a change in the Y-intercept.
You're done.
Right? If you know that Km stays the same, okay, find the plot that has no difference in the x-intercept.
You're done.
It's so fast. And that's the beauty of it. So let's get into inhibitors so we can get you hooked on Lineweaver-Burk like we are.
Absolutely, because I'm in love. But you're right. And so when we talk about inhibitors, I think it's important to know about why inhibitors exist, right? And this kind of goes back to the idea of regulation. Now we've talked about, I know in previous episodes, about homeostasis, right? Like how the body wants to be in balance, wants to be in this idea of homeostasis. We don't want to be too hot. We don't want to be too cold. We want to be just right. But in order to be just right, we don't want some things happening all the time. So for example, like we have in our cells millions of enzymes happening, all catalyzing reactions, but maybe we actually don't want those enzymes working all the time in all these ways. And so we have all these regulatory mechanisms, but one of them is by adding an inhibitor molecule. Now, an inhibitor is what they're going to do is going to inhibit that enzyme. That's what, again, the name tells you what they do. And so, but when we talk about these molecules inhibiting, there's different ways that a molecule can inhibit them. And that's what we're going to dive into. And I like for separating kind of the two overarching headings, right? There's some inhibition that's reversible and some inhibition that is irreversible. So let's talk about what we mean by reversible, irreversible. When we talk about something's reversible, that means that inhibitor can bind, but because it's reversible, it can come off. It can let go. Whereas if it's irreversible, this is an irreversible inhibitor, when it binds, it doesn't let go, right? It's just stuck there. And so when we talk about an irreversible inhibitor, there's sort of one type of inhibitor that on the MCAT, that's all what you really need to know about it. We call it a suicide inhibitor. When that inhibitor binds, it binds and doesn't let go. But what's important, the MCAT's going to expect you to know, is the bond that it makes. When you see this certain bond, that means you know it's not coming off. And so when this inhibitor binds, it binds covalently. It makes it binds covalently to the enzyme, and because it's bound covalently, it's not coming off. And that's why we say it's irreversible. And so this is important to note. That means for all of our reversible inhibitors, do any of them bind covalently?
No.
Absolutely not. If you ever see in a passage, like, it doesn't matter where it binds. Like, an irreversible inhibitor can bind on the allosteric site, can bind at the active site. If it binds covalently, irreversible inhibitor, done, it's a suicide inhibitor. But that means all these reversible inhibitors, the kind of the meat of today, which are reversible inhibitors, they have all sorts of interactions, ionic, hydrogen, hydrogen bonding, hydrophilic, hydrophobic. None of them, though, covalently bind is the key.
Yes. I always imagine it as the difference between, let's say the light is on. You could flip the light switch and turn it off. That's like an inhibitor, right? And you could just as easily flip it back on if the conditions were different. A suicide inhibitor or an irreversible inhibitor is like taking a baseball bat to the light.
Back to the light bulb. It's like, you're done now. You're not taking that back.
Yeah, it's not going to turn on because you've destroyed it. You fundamentally destroyed it. You can't, there's no going back from that. You can't piece it back together and make it work. Okay. So reversible inhibition is all about flipping the switch, so to speak. Or at least a lot of them are about flipping the switch. Some are actually just a major nuisance. So let's start our discussion off with our competitive inhibitors. We were talking about this. I feel like we both kind of agree competitive is the best place to start because it's the most intuitive in most ways. Although I am very partial, uncompetitive is my favorite. The drama is high with our uncompetitive inhibitors, but we'll start with competitive. The whole idea, right? We have an enzyme. We know it has an active site. It's got a whole, range of possible allosteric sites, other places that things can bind. A competitive inhibitor is going to compete with the substrate. So where is it going to bind?
Obviously where the substrate is going to bind, which is the binding site or the active site.
Yes, exactly. So competitive inhibitor, just very literally, like the substrate can't bind to the enzyme because there's something else, sitting in its spot, right? The
Mhm.
competitive inhibitor is already there, and therefore the substrate and the enzyme just can't get close together.
Mhm.
I want to be super clear. The enzyme itself is not active, but it's not because the enzyme is broken. It's just
Mhm.
because it can't grab onto the substrate and catalyze the reaction, right?
Mhm.
There's nothing fundamentally wrong with the enzyme here,
Mhm.
right? But it can't grab the substrate, right?
Mhm.
So what we see with the competitive inhibitor is usually it very closely mimics the structure of the substrate. Sometimes very specifically, you'll hear substrate analog. If you
Mhm.
hear that, you should think competitive inhibitor, right? It just
Mhm.
means that you look the same. And if you look the
Mhm.
same, you probably bind to the same spot,
Right.
right? But as far as KM and Vmax go, right, what this is doing
Mhm.
is it's preventing the substrate and the enzyme from coming together. Does
Mhm.
that sound more like something that would affect KM or Vmax?
Definitely something initially I'm thinking, well, it has to do with binding, so it has to do with affinity. So therefore
Mhm,
that's related to KM. It has to be.
mhm. Yeah. And is affinity going up or down?
Oh, well, I'm thinking first and foremost, well, I'm less likely to bind, so
Right.
affinity is going down.
Which means KM
Has to be going up, right?
is
They're
going
inversely
up.
related, right? So KM
Yes.
goes up, which I mean means affinity goes down. I like always kind of saying it as like I always kind of give the example of like a broccoli and a cookie. Like I have a broccoli and a cookie. Right?
Oh,
I
I
should
love
be eating the
broccoli. This is not
broccoli,
going to
right?
apply.
Oh, I am the exact. I have such a sweet tooth, such a sweet tooth. If I
Yeah,
have a
I have
broccoli
that
and a
too.
cookie, knowing that I have a sweet tooth, I am much more likely to eat the cookie and much less likely to eat the broccoli. My affinity for the broccoli has gone down. My likelihood that I'm going to eat it has gone down. Therefore, the KM is going to go higher. However, the enzyme itself doesn't change.
Yeah.
And so this is important when we talk about its ability, kind of like that kcat idea that we talk about, its maximum work. If I don't change it, right, am
Hmm.
I going to impact the maximum amount of work that it can do?
Nope.
No. So therefore, if I don't impact kcat, am I going to be impacting Vmax?
Nope.
Absolutely not. So this is what we say for a competitive inhibitor. Km increases because affinity decreases and Vmax does not change. A great way to think about it is that we can also, this is the one that normally people learn about in school, like you can outcompete the competitive inhibitor,
Yeah.
right? Where it's like you can add enough substrate so that you have so much substrate in relation to the inhibitor that you can just like outcompete it at the active site. And so you can still reach the same Vmax, you'll just need more substrate to do so.
Yeah.
And so I personally like thinking about this structurally, especially when it comes to the other inhibitors. I feel like it helps. But you can think about it both ways, both of them equally correct. Where Vmax isn't going to change nonetheless, but Km is going to change.
Yeah.
Mhm.
Vmax, and I don't know if we said it in this language before. Vmax occurs when we say the substrate is the enzyme is saturated
Great.
with the
Mhm.
substrate.
Mhm.
Meaning that's what I was alluding to when I said it's like drowning in substrate. It's
Mhm.
everywhere. It's outnumbered,
Mhm.
right? There is so much substrate that the enzyme cannot work any faster, right? It's overwhelmed by
Mhm.
substrate basically.
Mhm.
At Vmax, the enzyme is saturated with substrate because substrate is very high.
Mhm.
Imagine picking, a marble out of a bag and you have 5 blue marbles. That's the substrate. If you
Mhm.
had 5 orange inhibitor marbles, it's going to mess you up a lot,
Right.
right?
Right.
You're going to pick a lot of the inhibitors by accident. Again,
Mhm.
you don't know what you're picking. The enzyme can't really tell you apart. It doesn't have eyes, right?
Mhm.
It's just reaching out and binding whatever it can or grabbing whatever it can. If we then take 1,000,000 blue marbles that are the substrate and you still have 5 inhibitor orange marbles, are you ever going to grab that? Like,
Not really. No.
no, it doesn't matter because they're so outnumbered, right? And
Mhm.
that's what it means to outcompete the inhibitor.
Right.
Um,
Right.
but okay, we know a competitive inhibitor, KM goes up, Vmax stays the same. What would we see in our graphs then if we
Mhm.
if we applied it there?
Well, I'm just thinking about intercepts in Lineweaver-Burk. So I'm just thinking, okay, let's think about in my opinion, the easy one, which is Vmax. Well, Vmax is not going to change. Therefore, my Y-intercept is not going to change, right?
Mhm.
1 over Vmax is not, it's going to be the exact same. And then, okay, so that's the first, I think that's like the really important point with competitive inhibitors. How do you know if there's a competitive inhibitor on your Lineweaver-Burk? When you add the inhibitor, Y-intercept doesn't change. You're done most of the time. But maybe they give you 2 graphs where, oh, the y-intercepts are the same. Well, now I would look at my x-intercept. Now, this is where I think where the real difficulty of Lineweaver-Burk plots, because it's an
Yeah.
inverse plot. Because we have to think about this for a second. Because we just said a competitive inhibitor increases Km. But we have to recall on the x-intercept, it's 1 over km. And so we are increasing the denominator, therefore the number as a whole gets smaller, right? And so how that would look like on the graph, the x-intercept would shift to the right, right? Because 1 over km magnitude-wise would get smaller, even though the km is getting larger. And so that's how you would determine that we have a competitive inhibitor. 1 over km would shift to the right, and y-intercept would stay the same.
Yes.
Mm-hmm.
Yeah. And again, we'll see if we could get some pictures up here. But I mean, like you mentioned, if Vmax stays the same, it's competitive. It's competitive, at least compared to the other ones. And for your information, we're going to talk about 4 different types of reversible inhibitors. 4 types, 4 answer options. I won't say it's a guarantee, but vast majority of the time, if you get a question about inhibition in a Lineweaver-Burk plot, you're going to get 4 plots. One's going to be each type. Okay,
Yeah.
so they could throw in a plot that doesn't exist. It doesn't happen quite as often because of how nice it is that there's 4
Right.
types of Lineweaver-Burk plots with these 4 different types of inhibitors. So that's a competitive. Okay. The next one that is incredibly fun
That
to
you
talk
love
about.
so much. It's
I
funny.
love
I
it.
like the ones after this one. This is your favorite, definitely.
I'm gonna let you have fun with our mixed and non-competitives. I love our uncompetitive inhibitors because as someone who likes to imagine like the analogous situation in human life, because it helps me remember so much, uncompetitive inhibitors are hilarious. Okay, they are so funny. And let me explain first what they do, and then I'll explain the way that I see it.
Sure.
Right, an uncompetitive inhibitor, and basically all the rest of the 3, they're all allosteric, right? They're not binding to the active site. They're binding somewhere else, okay? They're binding to an allosteric site, but only when the enzyme and the substrate have already bound together. Meaning if you have an uncompetitive inhibitor and just the enzyme, there's no inhibition.
Not binding.
It will only inhibit when the enzyme and the substrate is together or when they are together, right? So it will bind to this allosteric site when they're together. And what it does is it locks them together. It absolutely locks them together, almost glues them together or handcuffs them together. They cannot fall apart. They're stuck, but they also can't do anything. It also flips the theoretical switch off. I think it's so funny to me because it's like, I want to catch you in the act is kind of how I see this, right? It's like, I am not going to, it's almost like, someone trying to catch their significant other cheating or something. Like, I'm just going to hang out here and wait until you're together. And then I'm going to catch you in the act when you're together, snap a photo that will be you two together forever. And yet it's a photo and you can't do anything, right? You can never be together, right? You're memorialized in this picture. Or like, you're handcuffed together. You can never go bowling or do anything fun together. You can never create a product because you're physically tethered. You can't do anything, right? No products can be made. Right? This does turn the enzyme off, which does mean kcat is affected. If kcat is affected, Vmax is affected. And specifically, the speed is going down, right? The enzyme is turned off. Vmax goes down. But where the silliness comes in, right, is the fact that the inhibitor is lying in wait, right? It's waiting to catch them in the act. It's waiting for the enzyme and substrate to already be together, and it is locking them together. Handcuffing, gluing, however you want to think about. It is keeping them together and they cannot fall apart, right? Trapping them together, which means the Km, well, actually, the affinity goes up like crazy. And this is why it's so important to talk about Km and Vmax is very different because the enzyme cannot work. Vmax and kcat are down, but because you've locked the enzyme and substrate together, the affinity is very high because the affinity is how much do you want to be together, basically, which means Km, affinity's high, is also dropping. And that breaks a lot of people's brains because they're like, higher affinity is good. How could that be an inhibitor?
Yeah.
High affinity, sure, but if the enzyme can't do its job, what's the point?
Mhm.
What's the point? Like there's no point to any of this.
Yeah.
And that's why I find it to be such a fun one to think about, a fun one to explain. Both Km and Vmax drops. That's not a good thing
Mhm.
because the enzyme doesn't work. It doesn't matter that you're locked together.
Mhm.
So that one is my favorite. I think it's really wonderful. And also, if you are struggling to remember uncompetitive and non-competitive, the last thing I'll say is uncompetitive unifies.
I was
Again,
just gonna say that. It's like the unified race brings together.
yes.
Yeah.
We have this is uncompetitive
Mhm.
that unifies and sticks them together. There's also a non-competitive, and that made me so frustrated for so long.
Right. Right.
Like literally, I get it that neither of them are a competitive inhibitor, but why is one and
And
why
one
is
is
one
non.
non?
Yeah. Yeah.
I would get those mixed up. So uncompetitors or uncompetitive inhibitors unify.
Unified, right? Unifying that
Yes.
enzyme and substrate together, catching them in
Yes.
the act. I love that. That's so cool. I love your stories. Oh, I love your stories. Wait until we talk about muscles.
Oh my
But yeah,
God.
and then so now we can think about, okay, so we know what we'll have to KMV max. Well, if we know about those two values, let's think about Lineweaver-Burk. Let's think about what Lineweaver-Burk is going to look like. And of course, the two places where we have to look is the X and Y intercept. So let's think, what do you think would happen to those 2 points?
So both are going down, Km
Mhm.
and Vmax. They're actually changing, and we'll talk about this in a sec. They're changing proportional to each other. So they're both decreasing. But
Mhm.
again, if the denominator is decreasing, the actual number is getting bigger. So they're shifting either up on the y-axis or to the left on the x. What's cool though is that it actually makes a parallel line.
The
So the
slope's the same.
slope doesn't change. And that's
Mhm.
important to know because when we talk about mixed, there's
Yeah.
another option that drops Km and Vmax both. Kind of annoying, but the slope changes. Here, it's
Right.
the exact same slope. It changes them proportional to each other. So
Mhm.
it's the same line, but just shifted to
Right.
the left and
To
up.
the left and up. But yeah, but I just like thinking about the intercepts. Like again, x-intercept is going to be magnitude-wise larger, y-intercept magnitude-wise is gonna be larger. Now that's the kind of thing I think that is tricky. It's like you're thinking, oh, Vmax is going down, therefore the y-intercept should go down. No, no, no. It's an inverse plot. So it actually gets higher, it gets larger. So
Yes.
that's the kind of trick. Be very careful. I sometimes think like in Lineweaver-Burk plot, whatever I think is gonna happen, the opposite happens. Oh, Vmax
That's
is
what
going
I
down.
say the same thing.
Yeah, or like
Everything's opposite.
everything's opposite. So you hear Vmax going down, oh, it's gonna get higher, right? Just flip your brain that way, and that's
I say
how
the
I
same
usually
thing.
think about it.
Yeah.
But now I get to talk about what I really love, right?
Yes.
So we've talked about competitive, gets in the way at the active site. We've talked about one of our allosteric inhibitors binds to another place, actually changes the structure, our first one being an uncompetitive inhibitor. But now we can talk about what I think is that one inhibitor that I think is forgotten about so much.
Yeah.
The mixed inhibitor gets no love, and it makes me
Mhm.
very sad because non-competitive inhibitors get so much love, right? Everyone, whenever I ask people about like what are the inhibitors, they say, oh yeah, competitive, non-competitive, uncompetitive, in that order.
Mhm.
And then they're like, yep, that's it. And I'm like, why? Because when we actually, it's interesting how the MCAT does this, but in a lot of other textbooks, and when I was learning about it, like in school, we actually framed non-competitive inhibitors as a type of mixed inhibitor,
Mhm.
which I think is strange because the MCAT says, oh yeah, they're two completely different things. But therefore, to understand it, we actually need to, before we understand a non-competitive inhibitor, we first need to understand a mixed inhibitor if a non-competitive inhibitor is a special type of one, right? And I think there's one point to know, especially everyone's memorized probably the Vmax and Km, but very few can tell me why is the thing.
Mhm.
So let's first talk about a mixed inhibitor, right? Mixed inhibitor is an allosteric inhibitor. So it doesn't bind to the active site, it binds somewhere else. But, okay, how does it bind? Because we talked about an uncompetitive inhibitor, the unified inhibitor can only bind at the enzyme substrate complex. When it's just enzyme, it's not going to do it, right? Mixed inhibitors, though, they're flexible. They can bind either the enzyme substrate complex or just the enzyme. They're not picky that way. They're not petty and like that where they're trying to catch their spouse trying to cheat. No, no, no. They'll bind to the enzyme no matter what. They'll bind to it whether the substrate's there or not. So, right, but the thing about mixed inhibitor is that it will have a preference.
Yeah.
It will prefer, like, again, it can bind to both, but it's like, yeah, I'd rather bind the enzyme substrate complex, or it might rather bind the enzyme. And this is an important idea because let's take each situation into account. Let's say it bounds the enzyme substrate complex. what do you think would happen to the affinity if it bound to the enzyme substrate complex of that specific enzyme?
Well, if it prefers the enzyme substrate complex, it's going to be a little similar to our uncompetitive inhibitor, right? It's mimicking that in its preference, and it's probably going to have the same effect on the KM, which would be to drop the KM.
Right, because if it's binding to the enzyme substrate complex, it's kind of locking them in together, kind of that idea. Increase the affinity, decreasing the KM. But okay, so it would decrease the KM if it bound to the enzyme substrate complex, right? Well, if it just bound to just the enzyme, what do you think it would do in that case?
So we didn't officially say this, but that's what a competitive inhibitor will do. A competitive inhibitor can't bind if an enzyme is already bound at substrate. So if that was its preference, it's probably going to mimic the KM patterning of competitive. If it will only bind when it binds to the enzyme alone, it's probably going to increase your KM.
Right, because it decreases the affinity, kind of like the competitive. This is why we call it a mixed inhibitor, because it's kind of a mix between an uncompetitive and a competitive. But while it can do both, it will have a preference. And so it will prefer either the enzyme substrate complex or just the enzyme. So if I asked you, Molly, just straight up, how does a mixed inhibitor affect KM? What would you tell me?
It depends.
It depends what it prefers. It depends what it prefers. If it preferred the enzyme substrate complex, while it can bind both, if it prefers the enzyme substrate complex, KM would go down. If it prefers the enzyme, it can bind both, but if it prefers the enzyme, KM will go up. Now, this is the tricky thing you were talking about before, especially when it comes to the Lineweaver-Burk plots, because now we have multiple options for a Lineweaver-Burk plot depending on our mixed inhibitor. Because like before, it was just like, it's always going to look like this for the other two, right? But now we have to take both situations into account. So let me give you a little bit of a test, Molly. I'm going to put you on the spot. We didn't find this. I'm going to put you on the spot. I'm going to give you a scenario, and you tell me whether this is a mixed inhibitor that prefers the enzyme substrate complex or if it prefers the enzyme.
Ooh, okay.
So I think this is kind of fun. So let's say I've got a Lineweaver-Burk plot. That's my line, Km, 1 over Km, 1 over Vmax. I just have that straight line. But then I have a new line. I've added an inhibitor, and now my line, the Y-intercept is now higher up on my Y-axis, right? And my X-intercept is now closer to 0.
Okay. So the way that I would do this, right, is think if y-axis, if basically my y-intercept is getting further from 0 and my x-intercept is getting closer to 0, those are opposite patterns, which means one must be going up and one must be going down. We didn't officially say this, but mixed inhibitors, no matter what, they drop Vmax. Okay. So if Vmax is dropping, Km must be getting bigger, right? Which one does that resemble? It would resemble a competitive inhibitor, which means that this must bind to the enzyme alone.
Right, absolutely. Because the Km, right, is getting larger. That's why the Y-intercept is getting magnitude-wise smaller. I'm going to have to preface magnitude because it's negative. But again,
that's why I say closer to 0.
Closer to 0, right?
One's further, one's closer to 0.
Right. But yeah, and that
is different directions.
And that is an important note that I didn't touch on here, but we have to recognize that when we talked about the competitive inhibitor, we said it doesn't change the structure, so it doesn't change the Vmax. All of our allosteric inhibitors bind someplace not at the active site, yet it's changing something at the active site. Like if this is big globular protein, this enzyme, it's binding on the other side, it is changing something at the active site. Therefore, all allosteric inhibitors must change the structure of our enzyme. Because all the allosteric inhibitors change the structure of our enzyme, change the structure of our worker, therefore, all the allosteric inhibitors must decrease Vmax. Right? All of them do. And so this is something I overlook because usually I completely forgot to mention that. And so thank you for catching that. All the allosteric inhibitors decrease Vmax. It doesn't matter which one, they all do. So mixed inhibitors, because they're allosteric, decrease Vmax, but how it changes Km depends on what it prefers. And so in the other scenario that we didn't mention, you could have a scenario where both the Y-intercept is now larger and the X-intercept is further from 0. While that sounds like an uncompetitive inhibitor, the main difference is that the slope will be different. The slope will be different. It will prefer, again, if we talk about this mixed inhibitor, it will prefer the enzyme substrate complex, kind of like an uncompetitive inhibitor, but how it changes Km and Vmax are disproportional. So therefore, their slope would be different. And this is, again, where why memorizing the graph shapes doesn't work. because of the nuances that we just talked about. There's not only one shape of a mixed inhibitor. It depends because there's variability.
Mm-hmm.
And so now I get to talk about one of my favorite things, which is the
Yes.
non-competitive inhibitor. Now, the non-competitive inhibitor, if it is a type of mixed inhibitor, a special type of mixed inhibitor, right? What do you think, Molly, can bind to if it's a type of mixed inhibitor?
It's got to be able to bind both.
Right? If a mixed inhibitor
Doesn't
can
have
bind
a
both.
preference.
Interesting, but doesn't have a preference is the question. So, yeah, but it has to bind. If it's a type, it has to have that same trait. It can bind both the enzyme and the enzyme substrate complex. But you might be asking, well, then what's the difference between a mixed inhibitor then? Well, the key here is that it doesn't have a preference. It's a very unique type of mixed inhibitor that doesn't have a preference. It will bind them equally. But let's think about the impact of that, right? Because of course it's an allosteric inhibitor. Since it's a type of mixed inhibitor, it will decrease Vmax. We know that for certain. But now we have to ask, what happens to Km? Well, if it's binding the enzyme substrate complex, what will that do to Km?
Km would drop.
Right? If it's binding the enzyme, what will that do to Km?
Would go up.
But if they're binding them both with equal affinity, what's the net effect on Km?
It is nothing.
No change to Km. It is so wild to me. Everybody knows that. Like when I ask and when I'm teaching a class, I'm like, okay, what happens to Km of a non-competitive inhibitor? Everyone's like, oh, no, Km doesn't change. Nothing happens to Km. And I ask, why? Crickets. No one knows, right? Then they say, oh, it's because it's allosteric. It doesn't impact the active site. I'm like, wait a minute, didn't we just talk about an uncompetitive inhibitor? Allosteric, it did, right? It did change Km. So it's this idea because it does change Km on the micro scale. Each individual enzyme, it is changing affinity. But on the macro scale, when you take all the enzymes into account, it net does not change Km, that equal kind of idea. And I love when people realize this, they're like, oh, it makes so much sense. Why would I memorize that? And that's my question too. This is not something to memorize. This is something to understand. But now, and that's why I like teaching it as a type of mixed inhibitor, because and I want to give mixed inhibitors some love because I think they get forgotten about.
And in every biochemistry class I've ever heard or seen, and even in many common MCAT textbook series, they'll teach you competitive, non-competitive, uncompetitive. And then they bring in mixed as like, there's this other thing that's weird and doesn't even have a preference, no pattern, don't even need to know anything about it. And it's like, we memorize the three that are clear. And then there's this kind of murky fourth that no one thinks is important. But I agree, flipping it actually makes sense. And then you can actually understand what non-competitive is rather than just taking it at face value and committing it to memory. And mixed really is a wider umbrella category of just things that can bind both. So what would the graph, this is our final type of inhibitor, what would the graph look like for non-competitive?
Well, in the same way that competitive, right? Because we know there's this one value that we can really zone in, same idea with non-competitive. We know Km doesn't change. So that's usually the first thought. If I'm looking for a non-competitive inhibitor, I'm looking at that X-intercept. 1 over Km, or negative 1 over Km technically, is not going to change because the Km doesn't change. The Y-intercept is going to be different because Vmax must change. Of course, we know that. But look at your X-intercept. That's not going to be any different. But then your Y-intercept must be higher because the Vmax is lower. So, but that's really the key. Look at your X-intercept. And if it doesn't change, you've got a non-competitive inhibitor.
Yes. So to give you guys the quick rundown, if you can remember, as far as enzymes go, if you can understand what each inhibitor, like what it will bind to, is that the enzyme alone, is it the enzyme substrate complex, and does it bind the active site or an allosteric? If you can remember that, you can then remember or learn or infer what Km and Vmax will do. If you know what Km and Vmax will do, you can get every Lineweaver-Burk correct.
Every Lineweaver-Burk problem.
Because you're just looking at the intercepts and you can reason if you need to, but oftentimes the intercepts alone, even just looking what is changing, they're both changing and they're changing in the same direction. Uncompetitive. Well, if slope is the same, I should say. Like you can fine tune it more and more and more if you need to, but oftentimes if you know how X and or how Vmax and Km change, you can pick your answer, period. You don't have to memorize the chopsticks and the swords and
I hate that. I hate them because again, people mix those up way too often. It's like, oh, what's the shape? Yeah.
That's why I hated it. This is like once you understand it, you can never get it wrong. If you understand what the inhibitor does, like what its mechanism is, where is it going to bind, how is it going to affect the enzyme. Km and Vmax you can infer. If you know those, you can quickly infer. Not even just like you can, it's quick to identify through Lineweaver-Burk. I actually think, I know a lot of us are more comfortable with Michaelis-Menten. It actually takes a lot longer to deal with inhibition on a Michaelis-Menten. To figure out what kind of inhibitor you're dealing with. If you see like without an inhibitor and another curve with, it's actually much more difficult. It takes a lot more steps. So go get some practice with enzyme inhibition. We've got 6,000 plus free questions in our question bank. We have even a separate area for enzymes. So definitely go get practice with that. Fundamental passages, fundamental questions with enzymes in biochemistry. Lots and lots of practice, especially now that we've covered enzymes as a whole. That being said, we are not even close to done with enzymes.
Oh my goodness. I am so happy that we're covering enzymes now, because this leads us really well into the next kind of real topic focus that we're going to hit on, because kind of what we're going to dive into for the next few episodes is going to be, I think, one of the highest yield biochem areas. I mean, I can't think of a higher yield biochem area. I mean, they're involved too, so I guess they're involved. But no, I think this is where I think a lot of people have learned this topic, that the next few episodes, probably 9 times at this point in their academic career, and still don't understand it. It was just always taught, memorize the steps. But we're gonna break them down. We're gonna break it down so that we're gonna make it understand. Again, Molly, what are we gonna talk about the next few episodes?
Well, the next few episodes, we are going over metabolism.
I love it. I'm so excited.
One of my favorite topics.
We've really built up to this point, right? Because we've covered all like the foundations that you need to know: redox chemistry, redox chemistry, right? All these it's like a crescendo of like topics. It's like, now that we understand these fundamentals, we now can understand aerobic respiration, which I'm really excited for.
Yes. I love talking about all of metabolism, but I'm partial. Actually, I don't know. I love glycolysis and I love the electron transport chain, but I also love the pyruvate dehydrogenase complex and the citric acid cycle.
Is this you fangirling over aerobic respiration?
I actually don't think I can pick. I was gonna say I love ETC, but I mostly love ETC because I get to teach redox, ETC, and electrochemistry in a 2 or 3 hour session, and that blows minds. But it's really not that hard. But we've talked about redox and electro, so I'm like, okay, will this be my favorite one? I don't think I could pick a favorite. Do you have a favorite metabolic process?
I'm a beta oxidation guy, to be honest. I'm not, it's not aerobic respiration, I know, but
I'm like a wallflower here. You're watching. You're participating too, but
I'm vibing. But I love aerobic. I love aerobic respiration, of course, but I think beta oxidation is really, really cool, just because of how how much energy you can get. Anyway, I'm nerding out now, but we will talk about this in future episodes, so get excited. And I think especially the content that we've covered today, yes, please review it. And I want you to realize, like, this fear Lineweaver-Burk plots that so many students have. I look at Lineweaver-Burk plots now, and I am so happy when I get so happy, because I'm like, oh, I see Lineweaver-Burk. There's nothing they can ask me that I'm not prepared for.
They've already analyzed it for you.
Yeah, like you see Lineweaver-Burk, look at the intercepts, you're done. You are legitimately done, and it's like case in point. So
a hug.
It's like a hug. I'm like, I know exactly what to expect if I see this. So again, we want everyone to have that same feeling, and so practice it. And then when you start looking at the intercepts, let us know in the comments how your practice has been going with Lineweaver-Burk plots.
Absolutely.
Can't wait to hear about it.
Yes, absolutely. We love hearing from you guys. And good luck with all of your practice over the next couple days, or I don't know when you're listening to this, but definitely tune in for our next episode where we're going to kind of do a broad overview of metabolism, and then we're going to zoom in on everyone's favorite process that you need to know in way too much detail, which is glycolysis. So we'll catch you in the next one, you guys. Until then, happy studying and have a great rest of your day.
See you, everyone.
Bye.